In other words, this time we need to look at all three components, x and y and z's. For any three-dimensional problem for a rigid body, we are having 6 equilibrium equations. 3 of them are force equations. So in other words, you can collect all the x component of forces equal to 0, all the y component of forces equal to 0, and all z component of forces equal to 0. These are the 3 equations based on Newton's law, so that the rigid body cannot moving. In addition, we need to make sure at a certain point all the x component of moments, y and z's must be 0, so that there's no rotation allowed. But for any three-dimensional problem, I'm not suggesting you to use these 6 equations. In other words, what you need to do is to collect this equation in terms of vector and then this equation in terms of vector. That's very straightforward, because this one vector equation is equivalent to these 3 equations. And then this vector moment equation is equivalent to this one. And you just need to write all forces in terms of vectors and add them together equals 0. You also need to calculate the moment of all forces at a certain point you pick, and then you do the cross product, add them together equals 0. So these are 2 straightforward governing equations we normally use. Instead of, at the very beginning, we're going to split with all the components. It's not very straightforward, especially when you talk about the x, y, and z moment components for those forces acting on certain point. It's not that straightforward. Instead, we just need to use the mathematics to help ourselves to finally establish those 6 equations. Okay? Before I talk about any examples, again, we need to introduce some kind of support for 3-dimensional setting. 3-dimensional supports are a little bit more complex. It's because you have to consider a third direction. But sometimes you can also use the common understanding, common sense to figure out. For example, this is called the ball support. So this is a part of the rigid body. And at this point, if there's a ball support, so what that means is at this point, because normally when we talk about wheel, we talk about balls, it's easy to move along these surface directions. But obviously, this one cannot penetrate into the foundation. So in other words, if you see this ball support, finally you only end up with one reaction at this point. So in other words, when you see the ball, you cut here, you gave one force acting on the rigid body. Same thing if you're now seeing a ball, however, you see this called a frictionless surface. So if this surface is a frictionless, so then this point cannot penetrate. So that's why you get the vertical support. But these 2 directions are free. So that's why you don't have any additional forces. So these are the easiest scenarios, in fact. Another easy one is what we call the cable as well. So if you have rigid body here connected with a certain cable, you just cut a cable and then you give the force always in the cable direction. Okay, so that's also straightforward. Sometimes you see this kind of wheel in 3-dimensional setting. This time we need to be a little bit more careful, because this wheel allows the rigid body to move very easily in this direction only. Let's say this is the x direction. But even with this wheel, you cannot easily move this one, because that's a sliding, right? It's a sliding movement. So this is a rolling movement. That's easy. Sliding is not easy. So that's why if you are seeing this roller on rough surface, the roller on rough surface, you have 2 reactions at this point on the rigid body. One is the vertical support, because you cannot penetrate this surface anyway. So that's why I have this one. But you also have the resistance in this direction, because if you try to move, you have to force this one will move in the sliding mode, which is not easy. So that's why you should have another reaction. So for this scenario, we have 2 forces serving as the reactions. You can sometimes also see this. This is very clear. You can easily rotate this one in this x direction, but it's not easy to move in this direction. And this one, you cannot penetrate this either. It's called a wheel on rail. So in other words, these 2 are having described mathematically using these 2 forces, Fy and Fz. Again, if we have a surface like this, but this surface this time is a rough surface. If this is the case, then obviously you cannot move in this direction, you cannot move in this direction, you cannot penetrate. So that's why you have these 3 reaction forces. But no matter what, all these scenarios, you can easily rotate. So that's why there's no, any of these cases, there are no moment resistances. Okay. Finally, this one is what we commonly is commonly used in structures. It's called a ball and socket. In other words, at this point, it's free to rotate in any direction, but this point cannot move vertically. It cannot move in the z direction. It cannot move in x direction. So this and this are in fact the same thing, what we call the three force components acting on this point A. But all these scenarios do not have the moment resistance, so that's why we never gave any moment. If we go back to look at, if we go further to look at some more complex scenario supports, sometimes we have to consider the reaction. For example, when we have this, what we call the universal joint, this we have to have some imagination. At this point, obviously, you cannot move in all three directions, so you have these three resistances in terms of forces. But this one, you just cannot rotate in this x direction. This is x direction. You cannot rotate because it's kind of contacting each other. But it's free to rotate in y direction and the z direction. So that's why this is a special design as what they call the universal joint. It's only not allowed to rotate in x component. So that's why you have a x moment resistance only. These are the cases, basically you can see, for example, like a hinge and bearing support, radical load only. For example, like this, what you can have is, at this one, it's not allowed to move in this direction, and it's not allowed to move in this direction either, unless you can break this rigid body, right? But it's free to move in this direction. So that's why this case or this case, the same thing. These are the two, the same. So there's no resistance in this x direction, no resistance, but y and z are not allowed to move. Furthermore, you can freely rotate in this x direction. It's a frictionless. But it's not allowed to move, rotate in y direction or z direction. So that's why these two scenarios can be described using this resistance in terms of two reaction forces and the two reaction moments. I want to talk about this one before moving this. This is another thing we commonly use called a fixed end. We already talked about fixed end in two-dimensional situations. This is a three-dimensional fixed end. In other words, the rigid body not only touching on the surface, going inside, so that this is to have resistance from the foundation, not only with the three component forces, but also three component moment. In other words, any direction is not allowed to move and not allowed to rotate. So this is somehow we frequently use as well. The last three scenarios are something like pin and bracket, or called the hinge and bearing support, axial truss, and radial load. So in other words, this one, you look at this one, or this two, you cannot move in any directions. So that's why you have these. Okay? And then the rotation, this is free to rotate in the x direction. If you move around this one, it's okay, or this one is okay, or this is free to rotate. So that's why you have a two moment resistance and the three forces. Obviously, we have to recognize sometimes it's not easy to figure out what are the corresponding reaction in terms of forces or in terms of moment. The best way I can suggest is either you can see any scenarios falling into one of these three categories, or sometimes you use your common sense to figure out as well. Okay, most of the time we have either fixed end or what we call the ball and socket support. And sometimes we have this kind of ball support. Okay, I want to talk about another example just to show you how we can solve a three-dimensional rigid body problem under equilibrium condition. This is one of the examples we can see from the book. A sign of uniform density, this one. The self-weight is 270 pounds, but this time, although we talk about self-weight, but in terms of pounds. In other words, you don't need to multiply with a 9.81. So 270 pounds is the self-weight of this sign of uniform. This rigid body is supported at point A, which is the ball and the socket joint. And we talked about this before, right? So if you want to plot it in a very accurate way, this is something to plot. On the other hand, most examples or questions, just simply use this one as a simplified plot to indicate ball and socket. In other words, this point is not allowed to move in any three directions, but it's free to rotate in any three directions. Further, this relay body is supported by two cables. One is at point E, one is at point B. So there's a cable BD, and there's another cable C supporting this uniform sign. So we need to, and obviously this is three-dimensional setting, right? So we need to determine the tension in each cable and the reaction at point A. So in other words, how can we calculate the magnitude of these two cables forces and also the reaction at point A? The procedures are the same if we want to compare with the two-dimensional problem. So typically, number one, we need to plot the free body diagram, and then once we got a free body diagram, we need to write down all the equilibrium equations. In other words, we have finally end up with the 6 equations, something like this. I'm gonna again help you solve this problem using the overhead projector, the document camera, so that you see all the details. But before I do that, I just want to briefly show you the free body diagram. So when we need to plot the free body diagram, we need to first identify the relay body. So obviously for this problem, it's very clear. This is the relay body. So the sign of uniform density, this one, is a relay body. So you just plot the relay body here. And then we want to look at how this relay body is interacting to outside world. Number one, there is a self-weight. It's 270 pounds. So first of all, we need to find out the geometric center of this relay body, the two diagonal lines having the common point, and then you gave this force acting on this common point going down. And then the magnitude 270, the direction is a negative in the y direction. And by the way, we set up the coordinate system. This is the x, and this is the y, and this is the z. So that's the self-weight. Also, this relay body is supported at point A. So this is called a simple three-dimensional pin support, or called the ball and the socket. In other words, you do need to have these three reactions: AX, AY, and AZ. And these are the unknowns. So leave it there. Finally, we have two cables. We cut these two cables, and then we gave these two reactions. One is called the cable EC, and then one is called the cable TBD. And we just need to figure out these forces. After we got all the forces, then we just need to write down those 6 equations. So I'm going to switch to the this overhead projector and to show you how we can solve this problem. Okay, so same thing. A sign of uniform density with the 270 pounds. That's a that is the self weight supported at joint A and also with 2 cables. And we need to calculate the 2 cable forces and also the reaction at point A. So the first step we need to do is to plot the free body diagram. So I'm basically just copying that free body diagram here. So we have this force, and we have these 2 cable forces, and then we have these 3 reaction forces. So once we plot the free body diagram, then our job is to use these 2 fundamental equations. But keep in mind, when we are writing these 2 fundamental equations, they are both in terms of vectors. Okay? So before I plug in all the forces into these 2 equations, in fact, what I'm going to do is to write all the forces in terms of vectors. Okay? So let's do one by one. First of all, we have this self-weight force. So the self-weight force, W, is characterized by the magnitude of the force with the 270 pounds and multiplied with the direction called lambda. But lambda is in the vertical direction, in the negative vertical direction, right? So then it's the 270 times negative j, because that's very straightforward. Otherwise, you have to pick 2 points. So simply, it's 270, negative 270j. Okay, so in the process, I don't have to write the pounds as a unit, but finally, when you conclude, you need to write a unit. So this is the first force, easy enough. Next one, we need to find some other forces. So let's say we try to characterize force EC, which is one of the cable forces, right? So this one. So any force as a vector can be written in terms of the magnitude TEC. This time I have to write TEC because I don't know the magnitude. So if I don't know the magnitude, I just write a symbol called TEC. But this TEC is different from the left-hand side because the left-hand has an arrow on the top. This is the vector. This is the magnitude. And then multiply with lambda. Okay, so our job is to determine the lambda. So what is a lambda? Lambda is a unit vector of the force direction. So going back to look at this one, or going back to look at this one, TEC, this is the cable, right? So you need to find 2 points to calculate lambda. So obviously there are 2 points, point C and point E. And then the force acting on here is from E to C. So in other words, this one should be C minus E, and don't forget to divide it by the norm, or the distance between these 2 points. Okay? So our job is to find out the 3 components of each point. What is the point C? Point C is here, right? So going back to look at point C, what are the 3 components? The x components, that should be 0. Y component 3, z component 2. Okay? And then minus point E. What are the 3 component point E? 6 and 0, 0. Any questions? So again, these are chapter 2 stuff, right? And then divided by the square root of 0 minus 6 squared, 3 minus 0, 3 squared, 2 minus 0, 2 squared, and then square root. Okay, so let me just write down the result for you. TEC negative 6 over 7, I plus 3 over 7, J plus 2 over 7, K. Any questions? So that's the first cable force. And now we need to move to the next one to calculate just another cable force, which is called TBD. So what is TBD? Same thing. The magnitude of force TBD multiplied with lambda. So TBD times lambda. What is lambda? This time, lambda should be determined by the other 2 points called point B, point D. Point B, point D. And the force direction is from B to D. So in other words, it's D subtract B. So what is the 3 component point D? 3 component point D, 0, 4, and then negative 8. Minus 3 component of point B. Point B, that's 6 plus 2, that's 8, and 0, 0. And divided by the distance between point B and point D, that's going to be negative 8 squared plus 4 squared, negative 8 squared, and then square root. Okay? So let me write down the result for you. BD. So TBD, negative 2 over 3, I plus 1 over 3, J minus 2 over 3, K. Any questions? Okay, so I think by now you should be very familiar with the lambda calculation. So now we got all forces, right? And finally we get another force, which is the reaction at point A. So let's say the reaction at point A, which is a vector as well, that's going to be the AXI plus AYJ plus AZK. These are the three components of the reaction. Okay, so once we got all these forces, we have a W here. You see W? Yes, here. We have W here, we have this, and we also have this one. We just add them together. So step number 7, for example, we need to collect all forces and set equal 0. Okay, so we do one by one. First of all, we have a W. So W, we have negative 270J, and then we have this one, plus negative 6 over 7 TEC in terms of I direction, plus 3 over 7 TEC in J direction, plus 2 over 7 TEC in K direction. Okay, so these are the three components from TEC, and then TBD. TBD are having three components, negative 2 over 3 TBD I plus TBD over 3 J plus negative 2 over 3 TBD K. And one more, this one, plus AXI AYJ AZK. And that's equal 0. Any questions? Okay, so then you just need to collect terms based on I and based on J and based on K. So this is I, this is I, and this I, right? Okay, so let me collect the coefficient in front of I. You finally end up with 6 over 7 TEC minus 2 over 3 TBD, and then plus AX multiplied with I. So that's the first one by sorting in terms of different groups. Second, we have this J, and J, right? So these four should form another group. So plus negative 270 plus 3 over 7 TEC plus 1 over 3 TBD plus AY J. Okay, and the last one, K. This is the K, this is the K, and this is the K. So plus 2 over 7 TEC plus negative 2 over 3 TBD and plus AZ K, and that's equal 0. So the left hand side with something times I, something times J plus something times K equals 0, then the only way you can allow this equation equal to 0 is to have anything in front of I, that's equal to 0, and anything in front of J, that's equal to 0, and anything in front of K, that's equal to 0. So one equation with a vector equation collecting all the force equals 0, you finally end up with the three equations. Okay? So once we're done with this, we just leave it for a while. Equation 1, equation 2, equation 3. We need to have the last step, which is to calculate the moment equation at the arbitrary point equal to 0. So let me just quickly show you. This is the free body diagram. So which point we normally choose? If we choose point A, I think that's a good choice because these unknown forces will not be involved. Okay? So let me just choose point A. And by the way, this is the arrow on top. So R cross F, and that's equal to 0. So we just do one by one, right? So this force RA will not be involved. The reason this one will not be involved is because this force is going through that point. In other words, it's R equals 0. So now let's go back to look at this force, TBD. So what is the moment of force TBD at point A? So that's going to be R cross TBD. Plus, what is the force TEC? That's going to be R cross TEC. And then finally you have the force is called the W. That's going to be R cross W, and that's equals 0. So we just need to find these three distance vectors. Let's do one by one. The first vector related with the force BD. So going back to look at this, the force BD. So what is the R? In other words, what is the distance vector from the point we want to calculate moment, that's a point A, to the point that force applied, that's point B. So from A to B. It's from A to B, right? From A to B, that means B subtract A. So B subtract A. But A is the original point. And that's easier, just B itself. So in other words, what is the B? You got the three components. The three component point B is 8I and 0 times J and 0 times K. So then that's it. So this R is basically from A to B, that's B subtract A. And finally end up with 8I. Any questions? Okay, second one, what is another R related with the force EC? So with the force EC, this is EC, right? So it's going to be that the distance vector is from A to point E. From A to point E, that's E subtract A. So then you basically have 6I. That's it. Right? Because point A is 3, 0, 0, 0. That's why you don't have to do the subtraction, in fact. Another R, which is the distance vector from the point you want to calculate the moment to the point the force applied on. The force applied on here. So that is the distance vector. So in other words, you need to find out, there's no point here, right? Let me create a point A, B, A, E, let's call H. So let's call this point H. So what are the three components of point H? That's going to be the horizontal, the x direction is A divided by 2, that's 4. 4I. And the y direction, total 5 divided by 2, 2.5. 2.5 going to the opposite direction is negative 2.5 J. And there's no Z component. Okay? Yes?
Couldn't you make that weight just go up in the axis and then just make it only 4 away?
Yeah, that's also good. Yes, because when you do the cross product, whether you want to say this point here or going point here, that's the same thing, in fact. Yes. Any other questions? Okay, so once we got these, you just need to have this one cross TBD, which you calculate from previous step, and use R cross another TEC, you got it from previous step. You have R cross W, you got it from previous step, and then you do the cross product. This one, in general, should give you 3 equations. However, one of these 3 equations should be automatic satisfied. In other words, the coefficient is 0. So that's why you basically end up with 2 equations for the second moment equation. But no matter what, combining with the previous 3 equations here and 2 equations here, you finally end up with the 5 equations. And how many unknowns do we have? We have 5 unknowns as well. So if you want to count, these 5 unknowns are AX, AY, and AZ, these are 3, plus the TEC, right? And also TBD, the TEC and TBD. So 1, 2, 3, 4, 5. You have 5 unknowns, but you do have 5 equations. Equation number 1, equation number 2, equation number 3. From these vector equation, you end up with another 2 equations. Okay? Because due to the time, let me just quickly show you from the slides. So the same thing. First of all, we calculate the force TBD, and then we calculate the force TEC based on this so-called magnitude times lambda, and then they basically, they didn't write, this one is given directly, so that they didn't write separately. So we just have all the forces together equal to 0, and then you basically collect these coefficients. They're all 0, as what I wrote as well. And when you take the moment at point A equals 0, that is something you need to do. When you further do the cross product, you get these two equations. In other words, the component in front of I is 0 already, so it's automatically satisfied. So that's why you don't have the number 6 equation. So with equation 1, 2, and 3, 4, and 5, you combine all of them together, you finally obtain these 5 unknowns. So AX is 338, and then AY is 101.2. AZ, you finally end up with a negative 22.5. In other words, you assume that AZ is in this direction. In reality, it is in the opposite direction. So that's why you have a negative sign. And the magnitude of TBD is 101.3, and the magnitude of TEC is 315 pounds. Okay? This is the typical three-dimensional problems if we want to solve for rigid body problems. Again, the key points are, number 1, you need to collect the force equation, and then you write in terms of IJK, and then you get the 3 equations. And then you also need to set up moment equation by picking up any point you like, and then you write down this vector equation. In general, you should end up with the 3 equations as well. So with all the combination of 6 equations, you should be able to solve for 6 unknowns. So that's why 6 equations solve for 6 unknowns. This is for three-dimensional problem. Okay? Typically in this chapter, all the rigid bodies we talk about are simple geometry, with a simple geometry. So that's why you can easily determine the self-weight point, like this one, because this kind of rectangular thin plate. That's why this point is the diagonal between these two. So that's why you can locate this point. Or if you go back to look at this problem, there's a self-weight. So then easily you can put the self-weight at point G, which is the center, because this is a simple geometry. Sometimes when I look at this one, this is a little bit more complicated rigid body. If that's the case, in this chapter, we have to tell you where the location is representing the self-weight. But how do we know this? In fact, we can find a way to calculate that location of the self-weight. It's called the gravity, the center of gravity. Okay, so next chapter, with chapter 5, I'm going to talk about how to find out the center of gravity, which is equivalent as what we call the centroid in mathematics.